Alright, in this video we're going to be talking about another passive circuit element which is called the capacitor. Now you should be familiar with capacitors from elementary physics and elementary electric circuits, but essentially a capacitor is a device that stores electric charge. And the most basic model is the one where you have two parallel conducting plates placed with an air gap in between. So perhaps something that looks like this. Now, if you have them connected to an electric circuit, essentially there's a short circuit here, but the charge is going to accumulate on each of these conducting plates. And so at some point, once the whole thing is charged enough, there's going to be an electric field generated that is going to flow from one side of the capacitor to the other. And so that's going to allow some of that electric current or that electric charge to flow through the capacitor. And that's what happens when it discharges, right? So that's a basic operation of a capacitor. In this course, we're only interested in how to use this for electronic circuits, so I'm not going to go into the physics of it. But the basic definition is capacitance is essentially the ratio of the amount of charge that you have and the potential difference. And then the next thing is going to be, this is usually measured in farads. But capacitance is it is usually quite small in the devices that you find. So I would say a more common units would be microfarads or nanofarads even. And that's the kind of thing that you encounter in regular electronic circuits. Now, the current across a capacitor is usually related to the voltage via this equation. So as you will notice, it's quite different from Ohm's law, where the resistance is a linear relationship. In this case, it is the capacitance times the change in the voltage. So this is the rate of change of voltage with respect to time. And right away, you can say that if you have a DC power supply, which is essentially constant voltage, you take the derivative of that and it's going to give you 0. So there will be no current flowing through the circuit. This is why capacitors and inductors, as we will see in the next video, they usually only work in devices where the power supply is not constant, so it is changing with time. But you can still use them in different senses. So in here I'm just gonna denote this as a generic power supply, so this could be a function of time. And if we wanted to express the voltage or the potential drop across the capacitor as a function of time, then we can rearrange this equation by integrating both sides with respect to time, and then essentially this is what we end up with. So we have 1 over the capacitance, and the integral, it is going to go from 0 to t if you're considering the initial time as 0 and then the final time is t, but this can have different definitions depending on at which time you start measuring it. But this is the most basic definition that we can come up with, and it is good enough for what we're going to do. Now, what we're really interested in knowing is, how do capacitors add in a circuit? Can we find such a thing as a total or an equivalent capacitance? And the fact is we can, and we can use Kirchhoff's laws to find that. So suppose we have a circuit like this with two capacitors in series, and we want to find out what's the total current across the circuit. We can use KVL because it's a closed loop of current. And so that KVL tells us that the sum of the voltages or the potential drops is going to be equal to 0. Now, we're going to use the same convention. We're going to make this a positive, negative, which corresponds to the flow of the current here. So, adding up all the voltages, we're going to be adding the potential differences based on this equation. Now, the first thing we know, since this is a series circuit, the current is going to be the same across each one. But basically what we need to know is, okay, so we're going to have this kind of arrangement over here. So the current is going to be the same for both of them. So we have the potential drop, which is in this case just the voltage supply. And then we have minus 1 over the integral of the current, and then 1 over C2 of the integral of the current. Now, obviously we cannot really do much with this. We want to find out the current. So one way in which we could do that is to actually take a derivative of both sides. So by taking the derivative, we get rid of the integral sign. So we end up with this expression. So we have dv over dt minus I over C1 minus I over C2. Since the current is the same, we can pretty much combine these two. And rearranging the equation algebraically, we arrive at the following expression. And the really interesting thing here is that this looks like a total capacitance. It looks like we just took these two capacitors and we combined them into a single one to get this expression, which is the original expression that we have here across a single capacitor. What this is telling us is that when capacitors are placed in series, they actually add as if they were in parallel. So this is the same thing configuration that you would get for resistors in parallel, but it turns out for capacitors it's actually the opposite. When you have them in series, you're going to have the sum of the reciprocal and then taking the inverse of that. So that's a really important result that we need to know about. Now, how do capacitors add in parallel? Well, we can apply the same thing, but in this case, I'm going to have the current splitting off at this node. So we have the total current I1, which is flowing in from the voltage supply, which I call V in. And it is going to split at this node into two currents, I2 and I3. Now that means we can apply KCL. The sum of the currents at that node should be equal to 0, which means that whatever is coming in must be equal to the sum of what is coming out, which is I2 plus I3. Now, we're going to use the definition of the current across a capacitor, and we're going to write down the expression in those terms. So in this case, we're going to have I1 is equal to C1 times dV1 over dt. So that will be the potential drop across this one, plus C2, derivative of the potential drop across this one. But notice that these two are in parallel. That means that the potential over here and over here is going to be exactly the same as it would be over here at the power supply. So essentially V1 and V2 are both going to be equal to V in. And that means that we can simplify this expression by just taking the sum of C1 and C2. So the interesting thing here is that capacitors in parallel actually add up as if they were resistors in series. So to summarize, what we can derive from these expressions is that capacitors in series add up according to this equation. So we take the sum of the reciprocals and then take the inverse of that. And capacitors in parallel add up simply by just adding them together like that. And that's a really interesting result that we're going to be making use of in later videos.